Hi, so today we're going to be looking at one-sided derivatives as we investigate or try to understand differentiation. So we have been looking at differentiating functions and finding the derivative of a function. And we did discuss in the past about how sometimes a derivative may not exist. Most cases so far we've seen where it does exist, but there comes times where there is a function that is non-differential, at least at one point it's non-differentiable. And I may have even said that an example of this is our common function f of x equals the absolute value of x, okay, and here was why. So we have points here and points here to kind of sketch our common function. So if you were to take any point that is greater than 0, it's going to be different, and the answer for the slope of our tangent line here is 1. Okay, here it's 1. And if we were to look at any values of x that are less than 0, okay, you would find that the slope of our tangent line would be -1. We would differentiate and find it be -1. But when it's 0, this isn't going to be a horizontal tangent. What happens at 0 is that you end up with two answers, okay? You have -1 and +1 as answers, and we went through that algebraically. If you have case 1, we get -1. In case 2, we get +1. We get two different answers, so it's non-differentiable at x equals 0. Okay, so we look at one-sided derivatives in order to determine whether or not our function is differentiable. So you should be copying, there's an A, B, and C. Okay, A is saying a function is differential on a closed interval from A to B if it has a derivative at every interior point of the interval. So that will work for a function that is like f of x equals x squared. Okay, even when x is 0, it's still going to be differentiable at that point. All right, but when, let's call it g of x. When g of x is absolute value of x, it's non-differentiable when x is 0. Okay? So it's something to kind of keep in mind, jot down part A. So part B, it says these limits exist at the endpoints. So the limit of f of a plus h minus f of a over h as h approaches 0 from the right is your right-hand derivative at x equals a being your left endpoint. Okay? And the limit of f of b plus h minus f of b over h as h approaches 0 from the left is your left-hand derivative at b. All right, that's because we're looking at an interval from a to b. So b would be your right endpoint. You're looking to do a left-hand derivative. So I said there was a C, and there it is. There's C. Again, if you need some extra time copying, just pause the video. Make sure you get this down. So C is saying that your right-hand and left-hand derivatives may be defined at any point of the function's domain. A function has a derivative at a point if and only if the function's right-hand limit and left-hand limit derivatives are defined, that means that they have values, and are equal at that point x equals a. So this is looking at a particular value, not just our endpoints of our interval, okay? And that's where we use one-sided derivatives, mainly, is to understand if it's differentiable or not differentiable at a point. Again, like our function of absolute value of x, all right? Then x would be a, 0 would be a in this particular case. And we would try to see what would happen. And what would happen is that our right-hand derivative would be 1 and our left-hand derivative would be -1. They are defined, but they are not equal. So this function is non-differentiable at x equals 0. Okay, and that's what C is saying. So let's go and see an example. Okay, so in this example, it says to determine if the function is differentiable at every point in the domain. Okay, so for the domain of this function, even though it's a piecewise function, is from -infinity to infinity, because if you look at what is described for your x values, we can use any negative value, we can use 0, and we can use any positive value. So we really don't have endpoints unless we're looking at a particular interval, but we're not. This is our domain, and that's saying at every point in the domain. So the issue is what exists, like what is going on at x equals 0. Okay, because if you look, that's where our function splits off from being a curve, a parabolic curve, to a line, okay, with a positive slope of 2. So we need to know if it's differentiable at that point, because therefore then every point in the domain would be differentiable, okay? We're good before 0 and we're good after 0. We just need to see what's going on at 0, okay? And the reason for this is because it's where it breaks off. Okay, so we need to do our right-hand derivative and our left-hand derivative, okay? So we need to find out what the limit of f of 0 plus h minus f of 0 over h is, as h is approaching 0 from the right. Now, it happens to be that our x value is 0, okay? That would not affect this if you're using this definition. It would still be h approaches 0 from the right for your right-hand derivative. Okay? And speaking of which, we also have to do our left-hand derivative. And this is where we use h approaches 0 from the left. Now, it looks like we have the same expression, but we have different functions, okay? So let's take a look at each one individually. So on the right-hand derivative, okay, we have to plug in just really h into our function. But if we're doing the right-hand derivative, 0 from the right, it's following 2x. Now, we're plugging in h into x, so let me erase that little typo. And that's our numerator, at least part of our numerator. The next part of our numerator is f of 0. That's where your function's defined at 0. So believe it or not, it's that top piece. That's where we can plug in 0. So be careful, because you have to know exactly what it's saying for each problem. And then when we do the left-hand derivative, it'll maybe make more sense. Okay, so what this here is the limit of 2 as h approaches 0 from the right. This answer is going to be 2. I'm just going to box it off so we can see it later. Now, our left-hand derivative, okay, we're plugging in essentially h into our function. If we're coming from the left-hand side, that is going to be the part that is x squared. So I'm going to do, again, the typo, h squared. And then we're going to subtract f of 0. F of 0 is where it's defined. And it's not defined, x equals 0 is not defined in the bottom function, it's defined in the top function. So hopefully you get the idea here. You have to read it and do it carefully. So what this gives us is actually the limit of h as h approaches 0 from the left. This is going to give us 0. Okay, so actually we find out because our right-hand derivative is not equal to our left-hand derivative, 2 doesn't equal 0, we can determine the function is not differentiable at every point in the interval, or I should say in the domain, because the function is non-differentiable at x equals 0. And this is due to the right-hand derivative and left-hand derivative are defined, but not equal. Okay, so just want to leave it up to you to do some practice, and good luck.